Hi guys, welcome again to my embedded DSP design tutorials. In this tutorial, I would like to discuss with you a very important component in the DSP chain, which is the DDS. So DDS stands for Direct Digital Synthesis. And the DDS I would like to specifically talk about more is the Xilinx DDS used in Vivado for generating continuous digital waveforms. So if you ever wondered how digital hardware creates smooth continuous waveforms, so it is the benefits goes to the DDS. It's thanks to DDS we are able to generate continuous waveforms on digital platforms. So the DDS is pretty much used in all kinds of DSP designs: modulation, demodulation, up conversion, down conversion, frequency shifting, and frequency mixing as well. So same concept, but anyways, so it is an equivalent to a local oscillator in the analog world. So in the analog world, we use a local oscillator for radio tuning, for modulation, demodulation, and in the digital world, we use DDS. Okay. So now let's talk more about the math behind the DDS, how the DDS generates continuous waveforms. So in the analog world, a continuous waveform can be represented by cosine 2 pi times f times t. So t is nothing but the sampling is 1 over sampling frequency. So t is is related to the is a sample time, like time 1, time 2, time 3, and that's related to the sampling frequency. So t equals certain number, like an integer, the first sample, second sample, third sample, and so on, divided by the sampling frequency. So t is nothing but n over f over s. You plug that back into the equation, and then the discrete samples equation becomes cosine 2 pi times f over fs times n. So now we need to represent n in terms of phase. So what we do, we map 2 pi over a number that can wraps around by itself. For example, a number that we can represent by a number of bits. In this case, with a simple case, let's take the number bits 2, like 2 bits, a number that can be represented by 2 bits, so it's going to be 4. So in this case, your n becomes 2 to the n divided by 2 pi, and then 2 pi cancels out, and then the equation becomes the cosine of f divided by fs times 2 to the n, right? Cosine of f divided by fs times 2 to the n. And inside the DDS is also an accumulator, so it accumulates. The first sample is the first phase increment. Second time, the phase increment multiplied by 2, multiplied by 3, and so on. So it accumulates. And at the same time, there is a lookup table that generates an amplitude that corresponds to each phase output. So let's say the phase turn out to be 0, then the cosine of 0 is 0. If the phase turn out to be pi, so that's going to be -1, and so on. So for every phase, you get an amplitude value that represents that phase. That's what I want to say here. So as you can look at the equation, the variables are interrelated to each other. So for fine tuning, for example, if you want to have a small frequency resolution, then you want to have your phase width, which is the 2 to the n, that's called the phase width. You want that to be bigger. If you have a bigger phase increment, then you will have a higher output frequency. So you can see, like, if you want to design DDS that synthesize a certain frequency, you can see, like based on your requirements, how these numbers will affect the outcome. Okay. So the equation, in my opinion, is pretty straightforward. I don't see much to talk about. But after you go through these slides and you look through my the posting that I did about the DDS and how it works, then you are more than welcome to send me any questions or comments on the channel or email, and I can answer your questions. So yeah, before we go to the implementation, let's quick look here at the this is a works example. Simple example, let's say if you want to generate a frequency of 1 hertz and your system is running at 4 hertz, and you want to have an increment that has a phase width of 4 bits, so which is 16. So the phase increment with the math turned out to be 4. So the first increment will be 4, 8, 12, and 16, and keeps wrapping around like that. And then inside the DDS, from the number it gets, for the case, for example, of number 1, so it gets pi over 2, so that's 0. And for the case of 2, it gets pi, that's -1. And case of 3, it gets 3 pi over 2, that's again 0. And case of 2 pi, it gets number 1. So the phase wheel is divided by 4, and every time we increment by 4, and we keep wrapping around. So again, it's a good example, very simple, and it can give you the feel how the DDS actually works and how it accumulates and generate the corresponding amplitude for each phase increment. Okay. This is another picture here that shows how the digital phase wheel looks like. So the frequency output is nothing but the sampling frequency divided by the phase width. I mean, 2 to the n is the phase width, and multiplied by the phase increment. So the phase increment times the sampling frequency divided by 2 to the n, or 2 to the phase width. So if you have 8 bits, so your phase increments would be 256. So we have in 256 slices. So we're counting by 8, I believe. Anyways, the phase increment, you cannot tell how much it's going to be. It has to do with the with the equation that you calculate. But anyways, you're going to have 256 if n is 8. So you're going to have 256 points on the phase wheel. Okay. Now let's go and take a look at our DDS, how we can make a synthesizable frequencies in the digital world. So the first thing you need to do, you would go make yourself an Excel sheet, and in that Excel sheet I will show you what you need to do. So in the Excel sheet, you specify, like in my case, how much your phase increment that you want. So for me, I want to have a phase increment of 1 kilohertz. So I want to have the first step 1 kilohertz, 2 kilohertz, 3 kilohertz, and all the way up to 40 kilohertz. So I used the equation here to calculate this phase increment. I did 1000 hertz divided by 100 megahertz times 2 to the n, and n in my case. And I show you why I got 30 there, just as per my configuration. So in my configuration, it turned out to be 30 bits. So, and I got this value here, 107,037. So the first step, you multiply this by 1. Second step, the DDS would do that. I mean, the code would be multiplied by 2. But anyways, so every step, there's an increment. So basically, you give the DDS the increment value that corresponds to the frequency you are targeting. So like here, we are targeting 1 kilohertz. Here we are targeting 2 kilohertz, 3 kilohertz, and so on. And you can see that here. So even here, like number 9 is roughly 9 kilohertz. So there's always some. If you want to have more fine resolution, you have to increase the phase width, and it can get pretty much close. So also all these parameters are related to each other again. So depending on what you want to do, so you can adjust them accordingly. Okay. So out of this whole Excel sheet, what I want I want only this number here, the phase increment, because that's all I want. This one is in my code. I need to give it to DDS to know how much, what frequency to generate. So you need to know this number and use it in your code. And I will show you how we will do that. Okay. Now we're gonna go to the Vivado and look at the IP core. So because I have right now a simulation going on right now, so I can share with you. So this thing is already open. So you go to IP catalog and you type DDS compiler and it should come out, and it's gonna look exactly like this. So DDS compiler. So the first page is like this. So you have to specify here your system frequency. In my case, is 100 kilohertz. Make sure you have phasor generator. Although I'm not going to use the phase, I'm just going to use the amplitude to generate the continuous waveform. I did not change anything here, although you can do that yourself based on your design requirements. So here I changed this just to get a higher dynamic range. I want to get 15 bits. That's why I did that. But if you change that, you can change that accordingly to it will target whatever number of bits you want for the output of the continuous waveform, and I want a frequency resolution of 0.1, and that's it. And then you go to the implementation, and here we have three options. So if you want to generate a fixed frequency, you select fixed, and that's simple. And actually, if you use fixed, the DDS itself will take care of the information for you. Will ask you what frequency do you want, and then that's it. You don't need this number. I'm talking about the phase increment. You don't need to calculate it. The DDS will calculate that for you. Okay. And here, make sure you are selecting phase offset programmability, make it to none, because this is a different configuration. It's out of the scope for now. I don't want to talk too much about it. And then for the output, it's up to you. What do you want? You want a sine or a cosine? So for my case, I just want a sine. It can also generate two waveforms for you, sine and a cosine. And also there's a polarity option here. So for me, I don't need negative cosine. Maybe in some applications you need that, so we have to do it. Here, I don't want to have the phase out either, so you can select that if you need to know the phase as well. So that's it, and I did not touch anything else. Here, I did not touch anything. However, make sure the output form, I mean, if you are targeting, like in my case, like two's complement, like you want a frequency that swings between, let's say, +1 and -1, so you want two's complement there. So latency configuration, I just leave that to auto, so possibly you can select configurable depending on your requirements. I did not want to have any clock enable or any reset. You could do that if you want. And at the summary here, when you go to summary, you'll be looking at something very important, which is the phase width. This 30 bits. 30 bit here is important because it's going to help you calculate the phase increments that you'll be using in your code. And that's about it. And then you hit OK, and then the Vivado will generate the IP core instantiation for you. And that instantiation, you use it inside your code, and I will show you how it looks like. Okay, now we cancel this, and we go to our code. And this is how our code look like. So this is the DDS instantiation. We have a clock. We said it's actually, this is not it. So this is on top level. Don't worry about that. Sorry about this confusion here, because I have DDS implemented as a module here. So that's what we want. So this is the instantiation, how it looks like. We have a clock. We have a phase T valid. So basically what you want to tell whenever you supply, we feed a value into the DDS, you want to tell the DDS, this is a valid input. So in my case, I set T valid to be high all the time. And then you want to feed the phase increment over here. As you can see, the instantiations give me 30 bits. However, in my case, I would never go to 30 bits. The maximum value in my case would be is only 30 bits, okay? And whenever there's data out valid, then you're gonna get a high, like a pulse high. And this is the output data that you are targeting in my case. It is 15 in my case, I remember, based on my configuration, but the instantiation gave us 16 bits, so that's fine. So that's all. So now we're gonna go to the top level and tell you exactly what you need to do. So the DDS for every step, so for every clock cycle, I'm running the system at 100 megahertz. So I expect the DDS to give me one sample for every clock cycle. And that means that for every clock cycle, I'm also need to tell the DDS, give the DDS a value for the phase increment, how much it is. Okay. So that was done. I mean, I did that two ways. I did that with a state machine, and I found that unnecessary. And in this implementation, I just used a simple, you know, a simple, a simple process. And I show you to make this big so everyone can see and what's happening. So that's how the process looks like. So we have a clock, so that's 100 megahertz. And we have a step count to keep track of how many steps. So as I said before, I want to go from 1 all the way to 41 because I know every step, you know, corresponds to 1 kilohertz. And there is something called dwell time. So dwell time meaning like for how long we want each frequency to persist. Because I started at 1 kilohertz, I want, you know, the period of 1 kilohertz just for one period cycle, one period, it's one millisecond. So I want to have a dwell time of 1 millisecond. So the first frequency will dwell for only 1 millisecond, but and you're gonna see only one clock cycle, one period. But the second time for 2 kilohertz, you're gonna see two periods, and so on. It keeps, so definitely the higher frequencies will be displayed more than once. So that's what happens. So yeah, so I specified a dwell time of 1 millisecond, and that 1 millisecond, how do you get it? That 1 millisecond, you get it by like because you have to specify a number of clock cycles. So depending on your clock system. So for me, this clock counter value turned out to be, let's see, what did they do here? So the dwell count that I have here, just bear with me. So it came out to be 100,000. So for 100,000, you can get 1 millisecond, and I want the maximum step to be 41. I did it here on the top as well. I might as well have everything here. Okay, good. And then we have the phase increment, as I mentioned to you guys, is 107.37, and it's going to be 30 bits. And this is the phase increment that we need to give to the to our DDS at every clock cycle so that it updates the accumulator. So nothing special in this process basically. So at reset, everything of course is going to zero. All registers are are reset, and then T value, as I said, is always high at the rising edge of my clock, and then basically you keep incrementing the dwell time, the dwell counter, and once the dwell counter hits the maximum value that I specified, then it starts all over again. So the phase increments, as you can see here, I called it the current phase increment. So this one, it gets updated all the time. I'm supposed to clean up a little bit here. It's already here. So I'm incrementing here and incrementing the step as well. And at the same time, I'm keeping track of how many steps. So once it hits 41, then you're gonna start another sweep. So basically you go from 1 all the way to 41, start another sweep. And also at the same time, you are looking at the dwell time as well. So the dwell time is for 1 millisecond. Like you don't want each frequency to last more than 1 second, 1 millisecond. So I'll clean up this code and leave it on my repository in GitHub, and you can follow through. And if you have any questions, please feel free to let me know. And let's take a quick look at the simulation. So it's still running, but you can see, actually I stopped it, but anyway, so you can see there is a sweep here. So 5 here, like 5 kilohertz. can run it here, but it's running right now. But it's gonna take a bit of time to reach 41 kilohertz. But it's doing what it's supposed to do, as I said. I don't want to again open the output of my filter to show you how it looks like, but anyway, it's doing what it's supposed to do. You can see low frequencies and then comes high frequencies. Um, so this is pretty much it, about DDS and how it works. So I would really urge you guys to, if you wanna get the benefits out of these videos, to go back and to my website embeddeddesign.org and read through the DDS, how it was implemented with the FIR, and repeat these tutorials or these projects, and try to change the requirements if you need to get the full benefit of it. And definitely, if you have any questions, please feel free to ask. um, Again, there's a lot of details in my website, and there will be a copy of this project that I showed you just now. Just you don't need to have the hardware. You don't need to have an actual real FPGA development. You can just do the simulation and see how things are happening. And this is how you get the benefits of these tutorials. I mean, you cannot just read through them and you think you get it. You need to you need somehow to get your hands dirty about this stuff to understand, to make it to make sense out of it. Okay. Again, thank you so much for your support. And if you have any questions, comments, please share with me. If you have any topics you would like to discuss in particular, please let me know, and I'll be more than happy to work on that. And definitely more useful content is coming, so please stay tuned. And if you like the channel, please subscribe and hit like. And I see you sometime soon for another useful video. Thank you for your attention, and talk to you later. Bye.